Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School. That's a boys' boarding school in Central Virginia. Our campus is beautiful this time of year. Historically, I would be spending my afternoons umpiring high school baseball locally or broadcasting Woodbury baseball games over internet audio. And I'm sad, so sad to lose these and other spring rituals. But as two of the four horsemen ride, I recognize that baseball simply is not important right now. So you might ask, why are we here then? I mean, I'm grateful to you for listening, for engaging over Twitter, for being the community that you and I both need right now. Let me give a shout out in particular to Cypress Ranch High School. Go Mustangs. They are arranging a virtual watch party with their physics teacher for every episode. But the question remains, why bother with physics in these apocalyptic times? I know many of you are here because your teacher or your parents are making you watch. That's fine. And some of you are making yourselves watch because you want to do well on the AP exam, to earn college credit, to demonstrate your knowledge of physics to yourself and to your teacher. I've no doubt that some audience members have come to love physics for its own sake. The universe is amazing, and AP Physics 1 lets you take the first steps toward understanding how the universe works. And some of you are here for the Edna fan art. Thanks, Aldous Gary. Your drawings have made me smile more than anything else these past weeks. Let me tell you an important reason why I'm here. Not just here today, but here in this profession. You see, science matters. Physics and chemistry and biology teach an understanding of the universe that is based on observable, measurable evidence. AP Physics 1 is a useful gateway to science because the experimental evidence in this course is human scale. It can be acquired in your classroom, except maybe for gravitation. The answers to physics problems aren't right because your textbook said, or because the president of the American Physical Society gave a press conference. Answers are only correct if they are supported by experimental evidence. Josh and I have been showing you not just answers, but evidence for those answers. That's science. Once you understand introductory physics and its human scale experiments, it's easier to understand chemistry and biology. The evidence underlying biology generally requires microscopes, PCR machines, DNA and electrophoresis, and all these more abstract techniques than just a photo gate or a spring scale. Nevertheless, biology is just as based on experimental evidence as is physics. And right now, there are people with media platforms, people in powerful political positions who straight up deny evidence. They'll state publicly that the sky is green. And even if you provide them with a spectrograph showing a peak at 470 nanometers, they choose to ignore science and believe what they want to believe. That has always been dangerous. It's downright deadly in a time of global plague. So I'm here for a lot of reasons, including a love of physics itself, a love of performance, a love of community, even the virtual community whom I cannot see behind that camera, a love for the relationships I've built with students and colleagues through decades of teaching physics. I'm here because I get paid too. But underlying everything is the hope that I can light a candle in the darkness that is science denialism, to help the next generations of students understand the meaning and power of scientific evidence. Now, to the physics. Today, we are discussing angular momentum and its conservation. We're going to start with a question from Wednesday. There it is. Josh gave you this. This diagram shows a top view of a child on a platform, and I'm going to be on a platform, even though I'm not a child, later today and do something very similar. And the question is, which of the following will allow the child to increase the angular momentum of the child platform system? If you want to Twitter what you think, I'm at Jacobs Physics. Please do check that out. And I will, at the end of class today, I will take a look at some of the questions that are coming through that Twitter feed. So in order to understand this problem, we have to understand what happens to the total angular momentum of a system of objects. That angular momentum, the total momentum, cannot change unless there is a net torque provided by something external to the system. When the child pushes on the platform, okay, the platform pushes on the child by Newton's third law, but the child and the platform are part of the system. Those are internal torques. What is causing an external torque to the child platform system? Nothing. Therefore, there is nothing that the child can do to change the total angular momentum of the child platform system. The answer is D. All right. We're going to do that experimentally later on. Here are the facts about angular momentum. They're on your screen right now. Feel free to take a screenshot and refer to these as we go on during today's show. We have two expressions for angular momentum. I'm going to get into these through a problem. I've got two major problems that I want to do today that both result in an experiment. Read this for me. We've got a disk. You can kind of see me in the corner of the screen. You don't have to see the details here. We've got a disk that's rotating, and then I'm going to drop a hoop onto the disk. And I want to know what is the final angular velocity of the disk and the hoop together in terms of everything else that was given, including the rotational inertia of the hoop, the rotational inertia of the disk, and the initial angular speed of the disk by itself. This question is asking for a derivation. Let's do a derivation. A derivation is an invitation to communicate your understanding of physics, not through sentences, but through mathematics. It's not about getting the right answer. It's not even about just doing a bunch of math with a bunch of different equations all over the place. A derivation requires the same level of organization and communication that a paragraph does. It's just that it's done in mathematics. If you're worried about your use of mathematics, try annotating your derivation. Write a couple of words here and there telling me what those equations represent. When we start a derivation, we must start with a fundamental principle of physics. That could be something on the equation sheet. That could be something that you have probably heard of before you got to physics class, like Newton's second law or conservation of linear momentum. In this case, since we have a collision, we want to use conservation of momentum of some sort. Since there's rotation, we want to use conservation of angular momentum. So I need to start with angular momentum conservation. This isn't a paragraph. I can read that and understand that as an AP reader. When we write angular momentum conservation, let's write an equation for that. I'm just going to use this notation here, meaning, hey, this is after the collision, this is before the collision. What objects in the system, the hoop disk system, have angular momentum before the collision? Well, the angular momentum consists of two terms, the angular momentum of the disk and the angular momentum of the hoop before the collision. Of course, the hoop wasn't rotating to start with, so that goes to 0. After the collision, the hoop and the disk are stuck together. So I'll just write one term for the angular momentum of them. And the formula I'm going to use for angular momentum here is I omega. I is the rotational inertia, omega is the angular speed. One more step. Let's take the rotational or the angular momentum of the disk. That's also I omega, but I have to answer in terms of the given variables and fundamental constants. Just a generalized I and omega isn't going to cut it. The problem stated I disk, I hoop, omega F, omega naught. So I have to be specific about what I's and what omegas I'm talking about. Well, the angular momentum of the disk to start with is I disk, and they called it omega naught, the initial angular speed. That equals the total rotational inertia of the disk hoop system. Rotational inertias are additive. So there you go. And we called that omega F, the final angular speed. What did the problem ask? It said derive an expression for the angular velocity at the end, omega F, in terms of all these other given variables. So that means I need to algebraically solve for omega F. I can't leave it here. There we go. That's the final step in the derivation. I've derived by starting with a fundamental principle of physics and showing mathematically my steps that lead to a result in terms of variables that were given or fundamental constants. Don't plug any numbers in. All right, that's the answer to the question. Of course, you guys know me well enough and you've heard my whole spiel at the beginning about experimental evidence. Well, we've got to do the experiment and see if this makes sense. I measured before the show today that the rotational inertia of the disk is 90 kilograms centimeter squared, and of the hoop, 50 kilograms centimeter squared. So if I plug in here, I disk over I disk plus I hoop is 90 over 140 is 0.64 times the initial angular speed. So this is not part of the derivation. The derivation asked for an answer in terms of given variables and fundamental constants. That's this. But now, in order to test whether that expression is correct, I made some measurements and I'm going to see if the final angular speed is in the neighborhood of 60-some% of the initial angular speed. If you recall from last class on Friday, I was measuring the angular speed here with a photo gate. Every time this little flag goes through the photo gate measures the linear speed of that flag, finds the distance between these two little gates and divides by the time it took, and it can make that measurement very precisely. And we talked about how V equals R omega, that was Josh's class last week. And because V equals R omega, we can say that whatever the linear speed is related to the angular speed. So let's take a look here. I'm going to get this going fast. I'll show you how I'm doing it. I'm going to keep this going fast, and then I'm going to drop this thing right in the middle. Except I'm going to do this while you're watching this. There you see the initial angular speed. Now you see the final angular speed. I'm going to stop recording. Now I know you can't see how precise this is. You can see that that it looks like the vertical axis value after the collision is, it could be about 64% of the vertical axis value before the collision, but I can tap it and it will tell me this is 2.1 meters per second. That's 1.4 meters per second. And 66%. I predicted 64%. Physics works. I'm a happy camper. All right, let's do another problem here. Read this puppy. In your laboratory, a ball collides with a wooden block. You can see me in the corner. Here's a wooden block. Here's a ball. I'm going to shoot this ball with a projectile launcher, boom, at the wooden block. And after the collision, the ball comes to rest and the wooden block goes off rotating. I give you the rotational inertia of this block. The question asks you, this is sort of a paragraph problem, you see. It's asking you to explain how you could use experimental evidence to show whether angular momentum about the block's center of mass, that's this position here, would be conserved in the collision. And you have to include information about how I will obtain or estimate the necessary data in the laboratory. So this is kind of a cross between a paragraph question and an experiment question. I have to talk about acquisition of data in the laboratory, and I have to create a coherent argument about how I could do this. We're going to check whether angular momentum was conserved. All right, let me stop sharing. Oh, I'll share the actual screen in a moment. I can't really do this live because this requires me lining up very carefully a projectile launcher so that it actually hits this and getting it hitting it exactly right so that this thing falls almost straight down. I did this already, thank goodness, right? And let's take a look. So let's take a look at this. Boom. And what's nice about this video is I can advance and go back frame by frame. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can go frame by frame to see what happens to the ball and the block. So back to the original question, how am I going to use this video and anything else I can use in my laboratory to determine whether angular momentum was conserved? Well, let's not just measure everything we can think of in the universe. That's not how we want to approach an experimental problem. Let's first figure out how we can make the measurement in principle. Let's do some mathematics. Let's do some understanding of the principles of physics in order to figure out what we need to measure. So I've got the block and the ball. Ball is moving that way. Let's assume for the moment that the block is or the ball is moving horizontally. Was it? It was probably moving a little vertically, but remember, make the most basic simplifying assumptions that you can possibly make as a start to any AP Physics 1 problem. An obsession with precision is the enemy in AP Physics 1. This block was stationary. So if we use angular momentum conservation, how do I know we need to use that? Because it asked us about angular momentum conservation and we have a collision. So angular momentum is conserved. Before the collision, the angular momentum is the angular momentum of the ball only, because the block is at rest. The block has no angular momentum. After the collision, we have the angular momentum of the block only, because the ball stopped briefly before it started to fall straight down. Again, that's pretty darn close to what actually happened in the video. So what formulas do we use for the angular momentum of the ball and the block? The block we just talked about. The block is an extended object, I omega, where that's the angular momentum of the block and the angular velocity of the block. The ball, though, the ball is not an extended object spinning like that. The ball is a point object moving in a straight line. The angular momentum of a point object, which you might have seen fleetingly at the beginning of this show, you can look at that screenshot later. You can also download my fact sheet. If you just Google Jacobs Physics, Just the Facts, AP Physics 1, you can download a fact sheet of every topic on the AP Physics 1 exam. Anyway, if you download that, you will find that the angular momentum of a point object moving in a straight line is mvr. So this is our expression for angular momentum conservation right here. The problem didn't ask for a derivation, though. This problem asked, how would you make measurements in your laboratory to check whether angular momentum was conserved? So really, we're putting a question mark there and saying, can we measure the things on each side here? And if so, how would we do it? M, mass of the ball. How would we measure that? Well, I'd take it over to my little scale over there and put it on there. I did that. It's 10 grams. That's easy. V. V represents the linear speed of the ball in meters per second. How am I going to get that? Well, if I wanted to do this again, maybe I could place a motion detector there, but even then, a motion detector can't pick this up very easily. The best way to do this, I'm going to share my video with you again. Let's go back to right before contact. Since I can go frame by frame here, I could measure on the video screen how far this ball goes in, say, 12 frames. How would I measure that? Well, I could take a ruler, and I could take this ruler and actually place that on the screen. Okay, but the screen is only a few centimeters long and the ball went farther than that. Well, I could prorate how far the ball seemed to go on the screen with the length of this rod. The length of this rod is 25 centimeters. So I've got a 25 centimeter rod. I can then see, knowing the scale of what's on my screen, I could see how far that ball went in 12 frames. Since I know that the video was taken at 240 frames per second, then I know that's 12/240ths of a second to go that distance. The block moves at constant speed before collision, so distance over time is the speed, voila. How would I write that up on an AP exam? I would say very briefly, I would measure the distance that the ball goes in some number of frames and divide the distance by the time, period. That's good enough. Remember, you don't have all night to write these questions. R, I want to bring us back here and talk about what that R term means. We know how to get M and V. How about R? R is not the radius of the ball, folks. That's the most common misconception here. R, when we use MVR, represents the distance of closest approach. R represents the closest distance between the line of the ball's motion and the axis of rotation. Where's the axis of rotation? The problem stated that angular momentum was going to be measured about the block's center of mass. R then, not the radius of the ball, but the distance of closest approach between the ball's line of motion and the center of mass of that block. We can measure that on the screen. The block is 25 centimeters long, so we can prorate that and find out how far the block how far down from the center of mass the ball contacted the block. So we measure that with a ruler on the screen. I is the rotational inertia of this rod as it rotates about its center of mass. I gave that to you on the problem statement. That's 2,400 grams centimeter squared. Wait, shouldn't we be in kilograms? No, don't worry about it. As long as you are consistent with units throughout, as long as you're not combining grams and kilograms, it doesn't matter. Furthermore, especially on a very short 45-minute AP exam, you're not going to be asked to be doing unit conversions. This isn't a math test. We're just telling me how would we make these measurements. Omega is the angular speed of the block after the collision. I need to share the video with you, and I'll show you how to measure that. Angular speed is measured in radians per second. This is a constant angular speed after the collision. So here's the collision. I'm going to advance frame by frame until this thing has rotated 180 degrees. We talked the other day about how there are 6 radians in a circle. So 180 degrees right there is 3 radians. This thing is now rotated 3 radians. How much time did it take? Well, I count the number of frames that I advanced, and I did that beforehand, and I found that I advanced 64 frames. So the angular speed of this block was 3 radians divided by 64/240ths of a second. There's my angular speed. And stop share. And I'm done. I've answered the question. Very quick review. This is our formula for conservation of angular momentum. I've got a point object moving in a straight line, so MVR. I've got an extended object rotating, so I omega. M is the mass of the ball measured with a scale. V is the speed of the ball measured with distance over time on the video. R is the distance of closest approach measured with a ruler on the video. I is the rotational inertia of the block after the collision measured, well, it gave us that, and we can figure out how to measure it if we take Physics C next year. And omega is the angular speed of the block after collision, which we measured by counting the frames it took to go 180 degrees. So that's 3 radians in 64/240ths of a second. Done. If you want to check this out later, feel free, see if this works. I've done this with a way more professional quality video that somebody else took, and it works beautifully, but you got to make sure that you do, that you're very careful with those unit conversions, and that's not important right now. All right. Let's move on to one more problem that we're going to do. Oh yeah, I'm in the right place. Look what I got here. Well, you can't look what I got here because it's underneath. I'll show you what I got here. All right, come on, Edna. She likes the rotating platforms. I'm on a rotating platform. You can't see the rotating platform, but I'm on it. You can tell. And what I'm going to do is I'm going to talk about the child platform system from the opening problem today. I'm going to talk about how a figure skater, a gymnast, a diver can change their angular speed, even though if they're not touching anything else, they are an isolated system that cannot change their angular momentum. Formula for the angular momentum of an extended object. Edna and I are a system. I'm not going to let her go. The only way to change our angular momentum is to have a torque provided by an external source, like this rod. Boom! I can change my angular momentum by touching this rod. But without touching the rod, I can't change our angular momentum. But I can change my angular speed. If I decrease our rotational inertia, then I will increase our angular speed. How could I, without touching anything else here, change our rotational inertia? Well, I can give Edna a hug. If I bring Edna from here to here, then her mass is no longer a long distance away from the axis of rotation, which goes through the middle of my head. No, rather, she's almost right on the axis of rotation. So her rotational inertia goes from something very big to something very small. Therefore, if our rotational inertia goes down, our angular speed must go up to conserve angular momentum. That's how a figure skater at the end of their show starts spinning slowly, slowly, and faster and faster and faster until you can barely see them as fast as they're rotating. But I'll do that for you here. I have to take this off for a moment so I don't get tangled. But watch how when I give Edna a hug, you'll see me speed up my rotational speed. One more time. You should have been able to see that. If you couldn't see it clearly, then rewind the video. I do this in my classroom, but when I do this in my classroom, in better times, I have students come up one at a time and just play with this while everybody else is working on something else. It's a lot of fun. All right, so what if I wanted to change my angular momentum? What if I wanted to change my angular momentum? Well, I can't if I want to hold on to Edna. But there's a way of changing my angular momentum that requires me to let go of Edna. This is the impulse momentum formula, the impulse momentum theorem it's often called, except rewritten for angular momentum. The change in angular momentum is equal to a time times a net torque, that is an angular impulse. But that net torque has to be applied by something external to the thing that's rotating. If I just keep Edna here, I can try to apply a torque, but you can't apply a net torque to yourself. That doesn't work. The only way I can change my angular momentum, in this case from 0 to something, is to let Edna go and let her push on me, and then I would be free to rotate. Well, I'm not going to throw Edna. Edna, that's too dangerous. I know you're a daredevil, but not today. Instead, I've got these inanimate 1 kilogram objects. I'm going to throw them. I've got little padding on the floor. I'm going to throw this such that it provides an external torque on me. Why external? Because this thing isn't going to be rotating anymore. The system consists of me only. This will provide a torque on me and will speed me up. It'll change my angular momentum without changing my rotational inertia. And then I'm going to throw the second one, and I'm going to go even faster because each time I throw this, I provide a torque on the mass. The mass provides a torque on me by Newton's third law, and therefore I change my angular momentum. All right, again, I have to take this off. Let's hope this works, and let's hope I don't fall down. That worked perfectly. The first time, it barely changed my angular momentum. I mean, it barely changed my angular momentum both times, but the first time you saw my angular speed go from 0 to something. The second time you saw my angular speed go from something to something even faster. I think you could see that. Anyway, time for questions, stories, and comments. If you'd like to go to @JacobsPhysics, then I will be able to see your comments. All right, here we go. Thanks to Brad Williams, as always, who is answering questions in the feed. How do you find the value of R in the experiment, says Harish. The value of R, in the experiment where the ball hit the wooden block. When we have the angular momentum of a point object, that's equal to mvr. This r is not the radius of the ball. That r is defined as the distance of closest approach between the object that's moving in a straight line and the axis of rotation. Since I defined the axis of rotation as the center of mass of this block, and the ball was moving like this, well, the closest distance of approach between the ball and the center of mass was right here. That's true even if the ball was back here. The r distance is the closest approach between the line of the ball's motion and the center of mass. Let's see here. Why do we measure 3 radians for the block instead of 6 radians, says Cody. Doesn't matter. I measured 3 radians because in the video, you only saw the block go this far. The rest of the rotation was obscured by the bottom of the screen. But I could have done 1.5 radians. The block went from here to here, and I could have done just that. That's 90 degrees. That's 1.5 radians. I could have divided that by the amount of time it took from there to there. Because the block was rotating at constant speed, any distance over any corresponding time would have worked. The bigger the angle, the more distance we can use, the more precise the results. Could we place a meter stick in the setup, says Nishta. That way we can see the distance traveled by the ball during the certain amount of time. Absolutely. Feel free. Stick a meter stick in. Make your own video. Most iPhones will, if you do the slow motion, they will record at 240 frames per second. That's easily fast enough to capture this video. Get a friend, and you can even just throw the ball. You don't even have to have the fancy projectile launcher. That said, this was the cheap version that I did very quickly. If you go to, there are other sources for much higher quality 1,000 frame per second video of similar experiments like this, and those are going to get you much more precision, and those do have a meter stick overlay that you can place right on top. Let's see. Daniel Z asked the important question: what is the difference between using MVR and using MR squared as the object's rotational inertia? Okay. First of all, I know he's not asking this, but I want to be clear that MVR is a momentum equation and MR squared is a rotational inertia equation. Okay, don't confuse the two. I don't think Daniel is. I think he's asking, why can't we just say, if we have a single object, a point object, why can't we just say that the point object's the point object's rotational inertia is MR squared, and then just use I omega, where we used MR squared for the rotational inertia? You can. It's just a very complicated thing to really understand that when an object is moving in a straight line, it does have an angular momentum about an axis that is not along the line of motion. How do you define the angular speed of this ball moving in a straight line? That's difficult. If you have like a coin rotating around this turntable, well, that angular momentum can be found by I omega, where I is just MR squared. But if you have an object moving in a straight line at constant speed, MVR takes away all the uncertainty of how to find the omega. Just MVR, where R is the distance of closest approach. That's why I used that formula. Let's see. Some comments about Edna. Yes, Edna is a hippopotamus. She's a very nice hippopotamus, and she does have friends, and she has her own Twitter feed even. Matthew Gilmore asks, am I an Arsenal fan? Yes, somebody did notice, come on you Gunners, in the corner of the screen. Yes, but like everything else, I can't root for Arsenal right now. Yeah, it's a lot of fun to watch their games. Let's see. Get a couple more here. If you would like to tweet at Jacobs Physics, I can answer the questions, and I will stay on Twitter for another half an hour just trying to answer these. Why does measuring distance from just the screen work in the video problem? It doesn't. You can't just look at your screen. I'll draw it up here. Here's your computer screen, and here is the block, and here's the ball, and we want to find out how far that ball went. Well, if you take a meter stick and you say, oh, okay, that went 8 centimeters. That's not what I'm talking about, because the ball didn't go 8 centimeters. But what you can do is you can say, look, I know the block's actual length is 25 centimeters. So on my screen, 8 centimeters corresponds to 25 centimeters. It's like the scale on a map. So when I measure this thing going 8 centimeters this way, it really went 25 centimeters. You're using a scale to figure out how far something went to get its speed. That's what I'm talking about. You do have to literally measure on the screen, but the measuring distance you get on the screen is not the same thing as the actual distance this thing traveled. What 2 high-ranking Klingon Empire officials were replaced by changelings during the 2370 during the war? I don't remember that one. I do remember that there were only 5 changelings on Earth during the crisis that was that happened on Earth when Sisko even suspected his own father in New Orleans of being a changeling. There were only 5 changelings, and they caused that much panic. It was very interesting. And did throwing the weight, this is Eva, did throwing the weight to change your angular velocity change your rotational inertia? And it changed your momentum, right? Because it was a torque for a certain amount of time. I considered myself as the system there. My angular momentum changed because, as you said, there was an angular impulse, a torque applied to me for a certain amount of time. Absolutely. Did I change my rotational inertia? Well, no, not unless I did that. When I threw the ball, I was still the same shape that I was before. The block was not part of me in that consideration. I considered myself and the platform as the only system. Therefore, the thing that I threw applied a torque to me. And I have the same rotational inertia as I did before because I had the same mass and I was in the same spot with my arm. So I did not change. My omega did change. And one more here. John Norris asks, doesn't throwing the weights cause acceleration for 2 reasons? It causes a third law reaction force, and it causes a decrease in, okay, we just answered that. I'm considering myself as the system here. The third law reaction force applied a torque, and that's what's going on here. All right, and if you did count the masses as part of the system, then we would find that the total angular momentum of the masses and me did not change until those masses hit the ground, because MVR then of the mass would be part of the angular momentum calculation. But I didn't consider those masses as part of the system. Defining the system means you can understand things a little better. All right. That's enough for now. Let me show you our problem for tomorrow. Got to share the screen again. I will be with you tomorrow. Josh will return next Tuesday. I've got you tomorrow and I've got you Monday. Tomorrow, we go back to the beginning. I always start my classes with forces in equilibrium. I'm going to give you some of the demonstrations I do on like the first and second day of my classes, where we measure forces in equilibrium. We talk about drawing free body diagrams. And this isn't going to lead into that. This is an angular momentum problem, but I'm going to start with this because it gives you another chance to practice angular momentum of a point object. Hope you can see that. I'll be with you at noon tomorrow. We'll be with you every day. And yeah, that's good enough. I will be on Twitter for about another half hour, and I'd be glad to talk to you. But after that, I have to start rehearsal for tomorrow's show when I'm going to be using this thing right here. Yep, you can see that. We'll be using that tomorrow. So until then, Edna, you want to ride that, don't you? I know you do. All right. Tomorrow, Edna is going to ride the cart. Until then, this is Greg Jacobs. Say goodnight, Edna. So long, everybody.